So, what is a paired samples t-test? A paired samples t-test is used to determine whether the means of two continuous variables, for example, before and after a treatment, from the same group of participants differs. So, here we're looking for one row per participant. They've maybe got like a pre score and a post score, or maybe you're looking at happiness. You gave some kind of drug treatment. So, you're looking at the score before you gave the drug and then after you gave the drug. But the trick here is that for each participant, the data have to be paired. There has to be some score at maybe time point 1 and then time point 2, or something like that, where you can pair the data in some way. This is a parametric test, so it assumes normality. And what this means is that your data must follow the standard bell-shaped curve with the highest amount of data in the middle and lowering off to the ends. And if you're looking for help running a paired samples t-test, we have the University of Guelph SPSS LibGuide, the Laird Statistics Guide, or the SPSS documentation. The trick with the paired samples t-test is it has multiple different names. So it might be called a dependent t-test, a repeated samples t-test, or a matched pairs t-test. So today we're just going to call it paired samples t-test. What are the assumptions of a paired samples t-test? We have 4 of them. The first is that your dependent variable must be continuous. Your second assumption is the independent variable must be categorical with 2 paired groups or conditions. So this is like that pre-post is very common for a paired samples t-test. The third is that your dependent variable difference, so a difference score, between your groups or conditions is approximately normally distributed. And I'll show you how to calculate that difference score today. And the fourth is that you should have no significant outliers in the difference, so the difference score, between your groups and conditions. So we'll do all this in the next few slides. Let's go. All right, checking our first assumption that your dependent variable must be continuous. Here we're looking at paired data. So we're going to look at both fake data 1 and fake data 2. So in this case, we're looking for each participant. They should have 2 observations, and it should be in 2 separate columns. And if we look in these columns, we've got some decimals, we've got some range of values. This data matches the assumption. So we've met the assumption your dependent variable must be continuous. Our next assumption is that the independent variable must be categorical. It must have those buckets of information. Also, they have to contain 2 matched groups or conditions. So if we look, for example, across these rows, we can look at participant 1. This person identifies as male. They've got data in fake data 1, and they've got data in fake data 2. That's paired data. So we can use this. We've met the categorical independent variable assumption because we've got participants who are either male or female. Okay. Our next assumption, normality and outliers. We can check these at the same time. So we're going to do both of these in the same dialog box in SPSS. The trick with the paired samples t-test version of normality and outliers is you're looking at the difference score. So you're going to have to do an extra calculation before you can do this. So what we're going to do before we even check normality and outliers is we have to calculate the difference scores. And we do that by clicking Transform, Compute Variables. So again, for the paired samples t-test, when you're checking normality and outliers, there's a calculation you have to do first. You have to get a difference score. So we're going to actually do a subtraction. So if we click Transform Compute Variables, that will open up the Compute Variables dialog box. And what we can do is we can write in the name for the test, or not the test, pardon me, for the variable. So here I've called it something very exciting. I've called it diff_scores. You can call yours whatever you like, but give it some meaningful name so you know what this is. So I know that this is a difference score because I've called it diff scores. And what you do is you do a little bit of math. In the numeric expression box, you're actually going to take your variables from the left side and do a subtraction in the numeric expression box. So here I've got fake data 2. I've taken that and I've dragged it or clicked the blue arrow to put it in numeric expression. I've clicked the minus sign because this works like a little calculator. So I've clicked the minus sign. And then I've taken fake data 1, and I've also dragged that into the equation. So I've got fake data 2 minus fake data 1. Once you've got your expression ready to go, you can click OK. And the trick here is it really doesn't matter which way you do this. You can either do fake data 2 minus fake data 1, or you can do fake data 1 minus fake data 2. The trick is it's just a different score between the two of them. The order doesn't really matter. Okay, so once you have done that, You should now have a new column in your spreadsheet called diff score. So we can kind of see mine hidden behind the dialog box here. It's calculated a new variable in our spreadsheet that we can use to assess normality and outliers. And I think you've seen this before, but we can click Analyze, Descriptive Statistics Explore. And what we're going to do is take that difference score column that we just calculated. If you don't have a difference score column, you have to go and make one. But we're going to take that difference score column and we're going to put that through the Explore procedure to check for normality and to check for outliers. So again, Analyze, Descriptive Statistics, Explore. That will open up the Explore dialog box. And what you're going to do is you're going to take your difference score variable that you just created, so whatever you've called yours, ours is called diff_score, and you take it from the left side and you put it where it says dependent list. If your variables have all been set up properly within SPSS in variable view, this should have a little yellow ruler because a continuous variable minus another continuous variable should give you a continuous variable, and the yellow ruler signifies that this is continuous. So we put difference score under dependent list and we click plots. There's a few choices you're going to want to make here. Under descriptive, you're going to uncheck stem and leaf. We don't really do those much anymore. You're going to check where it says histogram because you want to do some visual inspection. And importantly, you're also going to click where it says normality plots with tests. This one's key because this is going to give you a statistic. And when you've done all that, you click continue. That's all you need to do, so you can click OK, and that will run your normality and outlier checking in SPSS. If you have clicked those buttons, you will get some output. The first thing we're going to look at is normality. So if you scroll partway down your output file, you'll get a tests of normality table. And we can use this to check a statistic to see whether our difference score passes normality. If you have more than 50 observations per group, you're going to look on the left-hand side where it says Komglemarov-Smirnov. If you have fewer than 50 observations per group or per in your difference score column, you're going to look where it says Shapiro-Wilk statistic. So we're going to be using the Shapiro-Wilk because we have 30 observations. And what you're looking for is in the SIG column. If your p-value is less than 0.05, you have failed the assumption of normality, which means you cannot use the paired samples t-test. It would be inappropriate to do so. Here we can actually see our Shapiro-Wilk statistic. We've passed normality because our p-value is greater than 0.05. So using a statistic, we've passed normality. We can also do visual inspection. So if you scroll a little bit lower, you should also see a histogram. What we're looking for here is if you squint a little bit, this histogram should follow our approximate bell-shaped curve from before. So highest amount of data in the middle with lowest towards the ends. So this one's not perfect. You can see that, yeah, most of the data is in the middle, but there's something kind of weird going on the right-hand side. But if you squint a bit, this looks like it passes normality. It's approximately the right shape. And in conjunction with the Shapiro-Wilk statistic, you're okay here. One last piece of visual inspection before we move on. We can also look at our QQ plot. So we have a line going across the page, and we've got a bunch of data points. Yours are probably blue. I made mine red for the presentation. But you've got a bunch of data points, and you're looking to see, are those points close to or touching the line? If yes, you've passed normality. If no, if a bunch of the points are pulling away from the line, you've probably failed normality. So here we've passed our assumption of normality. Excellent. The next thing we can do is in the same output file, we should also have a box plot to help us look for outliers. And again, this is on our difference score. So our box plot is another way to check for visually whether we've got some outliers going on. We've got a median, the black line in the middle, our interquartile range, and our whiskers. And what we're doing is we're looking to see, do we have any data points outside of those whiskers? They'll be identified as either a circle or a star with a number. The number next to those circles and stars indicate which row of your data set might be an outlier. The circle being a regular outlier, the star being an extreme outlier. Here we don't have any outliers identified using the box plot method. There are other ways to do outlier checking in SPSS or other software options as well, but SPSS makes box plots super easy, so it's just the fastest way to do it. In some fields, you might also do something like the mean and the standard deviation, but we're not covering that today. All right. If you have passed all of your assumptions, today we have passed all of our assumptions, so it's okay for us to do the paired samples t-test. If you have passed your assumptions, you can move on. and you will click Analyze, Compare Means and Proportions, Paired Samples t-test. If you have not passed all of your assumptions, you might need to do something to change that. So if you have outliers, maybe you remove some outliers, you check your normality assumption again, for example. If you failed normality, but you've got no outliers, maybe you have to switch to a different test. But if you've passed all your assumptions, reminder, always check your assumptions. You're going to click Analyze, Compare Means and Proportions, Paired Sample t-test. That will open up our Paired Samples t-test dialog box. A few things you have to click here. You're going to take your fake data 1 variable and put it where it says variable 1. And you're going to take your fake data 2 variable and you're going to place it where it says variable 2. You want those to be on the same row. You can do multiple of these tests at the same time. So which tests you're comparing have to be on the same row. Here we're using row 1. If you also wanted to compare fake data 1 versus fake data 3, you could put those then on row 2 and it would run both tests for you. And here as well, it doesn't matter whether you do 1 and 2 or switch them and say 2 and 1. The order doesn't really matter. If you have that all set up, you're going to click OK. It's pretty easy. And you'll get a fairly large output with multiple different tables here. So the first thing you're going to see under your t-test table is paired sample statistic. This gives you your mean, your n or number of observations, your standard deviation, your standard error of the mean, some standard descriptive statistics of what's going on within these two variables. The next, you'll see the paired samples correlations table. Don't really have to do much there. I don't normally look at that one. The thing you care a little bit more about is the third table, the paired samples test table. It's got a bunch of different information here. It's essentially taking your two variables and saying, in general, is one of our variables higher or lower than the other? If you're looking for both higher and lower, or if you don't know which direction you might find a difference in, you're going to look where it says two-sided p. This is pretty standard. If you had a previous hypothesis about what might be going on and you think that, for example, 1 is going to be higher than 2, you might do a one-sample t-test. But generally, if you're not sure, use a two-sided p. It's pretty standard. So this table gives you stuff like your t-value, your degrees of freedom, and both a two- and a one-sided test. All of that information will be useful if you're writing it in a paper. But here what we're looking at is our two-sided p in our significance section. And what this tells us is if p is less than 0.05, we have found statistical significance. And what that means is that one of our variables is higher or lower than the other. So here our p-value is less than 0.001. We found statistical significance. And what we can do is we can actually look up at that first table I talked about and look at the means to see which one is higher than the other. The p-value tells us they are different. The means can tell us in which direction. So our fake data 1 variable has a mean of 87.1, and our fake data 2 variable has a mean of 92.5 if you round that. So this means fake data 2 is higher than fake data 1, and that's backed up with our p-value. There's one other important piece of information that you might want. It's in our last table, the paired samples effect sizes table. What we're looking at here is the Cohen's d value. Cohen's d is a measure of effect size. How large is this effect? All right, so that is how you run your paired samples t-test.